Hey everyone. So complex analysis gets kind of used fairly frequently in differential equations, and I wanted to just make a video kind of going into detail on some of those things, some of the connections between the two subjects of complex and diffie-q. So we're not going to go super deep into this stuff. It'll be a little bit surface level, but I do want to at least kind of hit the major points. So R denotes the set of real numbers. This is surprisingly difficult to actually define this formally, so we won't do it. C denotes the set of complex numbers. So this is pretty easy to define if you take for granted the definition that like the reals have already been defined. So the complex numbers are just the set of numbers of the form x plus I times y, where x and y are in the set of real numbers. So things like 2 plus 5i, that's a complex number. Let's see, I itself is a complex number because you could write it as like 0 plus 1 times I. And similarly, the number 5 is a complex number because you could write it as 5 plus 0i. Any real number is going to be a complex number. Like pi is a complex number, square root of 2 is a complex number, so on and so forth. Anyway, I is just a number that satisfies the equation I squared equals -1. We don't usually write I equals, I guess you can say I is just the square root of -1. That's, I mean, I guess fine, but remember, like, you know, when you take the square root of a number, there are two choices there. So square root of 4. If you take the square root of a number, it could be like plus or minus that number. So technically there's like two choices to be made here. And so typically we'll just say I is just a number that satisfies I squared equals -1, and you make a choice of what that number is from the start and then build your entire system out from it, right? So I is, or complex numbers can be represented graphically in a two-dimensional plane. So you have your real axis and your complex axis. Your real axis is basically just the real line. So any real number would go over here. So like the number 5 was here. The number like 2i would be up here. This would have like, you know, the y coordinate 2, but it represents the complex number 2i. You could represent the number like 5 plus 2i just by going 5 over to the right and 2 upwards. So just like in polar coordinates, all complex numbers can also be represented in the plane with coordinates r and theta, where r represents your distance to the origin, and theta is going to represent your angle with the positive real axis. So note that your angle theta, like any two angles that differ by 2 pi are going to represent equivalent angles, right? Like 0, 2 pi, 4 pi, they all represent the same angle. So just keep that in mind when you're defining things or looking at these numbers. You can use them interchangeably. And again, just like in polar coordinates, you get a nice conversion between Cartesian and polar, and you get a nice conversion between representing complex numbers of the form x plus iy and using the angles, the coordinates r theta. So x is equal to r cosine of theta, and y is equal to r sine of theta. And if you haven't seen polar coordinates in a while, that just comes from this triangle right here. You can just say like, all right, well, cosine of this triangle right here, cosine of theta is equal to x over r, and sine of theta is equal to y over r, and so you get this equation right here. So you can basically just build out these equations. Okay, so here's the first major fact. This is called Euler's formula, or Euler's identity, or however you want to call it. And it just says the following. So for all angles theta, for all real numbers theta, e to the I theta is equal to cosine of theta plus I sine of theta. And so this basically gives us a way to represent basically, let me say it like this. It gives you like a way to like sort of go between representing a number like 2 plus 5i and representing a number with these r theta coordinates. And I'll show you kind of like what I mean by that in a little bit. But before I get to that, I want to actually prove this to you. I'm going to show you two proofs. They both kind of highlight some of the connections between the fields of complex analysis and Diffie-Q. So the first proof I'll give you is more of a Diffie-Q flavored proof. So it starts with just defining y to be cosine of theta plus I sine of theta. And we're going to do some stuff and conclude that if y is equal to this, then y is also equal to e to the I theta. And so to do that, we'll start by computing dy d theta, just taking the derivative. Derivative of cosine is, derivative of cosine of theta is negative sine of theta. And then the derivative of I sine of theta is I cosine of theta. And so if we then multiply by, I'm going to multiply this equation by negative I. And why am I doing that? Well, because this equation right here is very similar to this equation right here, except like the i's, the I is like showing up attached to like a different thing on both of them. So if you multiply by an I, it might switch where the I is effectively. And I'm also multiplying by a negative because I've kind of seen this before, and I know that we're going to want to like multiply by a negative at the end of the step anyway. So if we do this, we'll get, so negative I times negative sine becomes positive I times sine of theta. And then negative I squared cosine of theta. But remember, I squared is equal to negative 1, and so you get this double negative right here, which gives us I sine of theta plus cosine of theta. But if we just rearrange this, just cosine of theta plus I sine of theta, this is literally just equal to what we defined y to be from the start of this. And thus we get that negative I times dy d theta is equal to y. All right. So from here, I'm going to bring this I over to the right-hand side. How do I do that? Well, I'm just going to multiply both sides of this equation by I. Usually when you just usually when you want to move an I to another part of the equation, you can't really divide by I. What we do instead is you just, I guess you can divide by I, but it is more useful to just multiply by I on both sides, because then it's easier to say like what I times y is instead of like 1 over I. It just makes more sense. Anyway, on the left side, negative I squared. Again, this is equal to just positive 1 because I squared equals negative 1, and then we have a double negative. So we get dy d theta equals I times y. And so from here, this is just a differential equation that we can solve. And so how do we solve this differential equation? This is like one of the more basic ones. I'll just do it really quickly. So this is a separable dE. So you can divide by y on both sides and multiply by d theta on both sides, and you get the following. And so you can integrate both sides. You get ln of absolute value of y equals I times theta plus a constant. And then you can do e to the power of both sides, and you'll get absolute value of y is equal to just a constant times e to the I theta. And then you can also just drop the absolute values because it's like, plus or minus a constant is still a constant. And so you get that y equals a constant times e to the I theta. What should that constant be? Well, remember that y equals cosine theta plus I sine of theta. Well, over here, we can say, like, all right, well, what is y of 0 equal to? It's just equal to c times e to the 0, or just c. And by our original definition of y, move that, y of 0 is cosine of 0 plus I sine of 0. But sine of 0 is 0, and cosine of 0 is 1. So we get that y of 0 has to equal 1. And we already know that y of 0 is equal to c, and therefore our value of c is equal to 1. And hence y is equal to 1 e to the I theta. So that's one proof of it. I'll show you one more proof, and this is a power series flavored proof. So recall a couple of common series you'll see, are power series you'll see, Taylor series, I guess. I'll just call them power series. E to the x, sine of x, and cosine of x can be represented as follows. So e to the x is equal to x to the n over n factorial, just the sum of those terms from 0 to infinity. Sine of x is is an alternating sum of x to the 2n plus 1 over 2n plus 1 factorial. I say alternating because of the negative 1 to the n. And then cosine of x is an alternating sum of x to the 2n over 2n factorial. If you were to write out the first couple terms of these series, x to the n over n factorial, that's equal to 1 plus x over 1 plus x squared over 2 or 2 factorial, and then x cubed over 3 factorial, so on and so forth. Sine of x, that would be, so n equals 0, this term goes away, then you get x to the 1 over 1 factorial, and then minus would be x cubed over 3 factorial, and plus x to the 5th over 5 factorial, so on and so forth. And then cosine would look like 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus, so on and so forth. All right, so based off of this, what is e to the I theta equal to? So e to the x is equal to this. So e to the I theta would just be, well, you can just replace x with I times theta. So we get the sum of I theta to the n over n factorial. And so if you were to write out these terms in the same way we did over here, I'm going to write out a couple of them, quite a few actually. So it'll be 1 plus I theta plus, it'll be I theta squared, or I squared theta squared over 2 factorial, and then plus I cubed theta cubed over 3 factorial, and so on. And using the fact that I squared is equal to -1, we'll see, we'll end up introducing like a bunch of negatives here. I actually think I want to write a few more of these out. Okay, so I squared is equal to -1, so this becomes minus theta squared over 2 factorial. I cubed is equal to negative I, because I squared is -1, and then you get that I left over. And then I to the 4th is equal to just +1, because I squared is -1, so that squared is just +1. And then we'll get I to the fifth is just equal to I. And I to the sixth is equal to negative, it's basically just equal to I squared. Like every 4 it repeats. Like if I squared is equal to -1, then I to the fourth is equal to +1. I'm going to write that in parentheses. So then this is minus I squared. Oops, sorry. Just minus theta to the sixth over 6 factorial, so on and so forth. Okay, so this series, a bunch of the terms in there are going to have an I attached to them. We're going to separate them out. So we're going to like rearrange the terms of the series here. So we're going to take like the even terms and the odd terms and then separate them. So this is 1 minus theta squared over 2 factorial plus theta to the fourth over 4 factorial. And then minus theta to the sixth over 6 factorial, plus so on and so forth. And then the I terms, I'm going to just factor out an I from all of them. So I times theta, and then minus I times theta cubed over 3 factorial, and then plus theta to the fifth over 5 factorial. The next one will be minus theta to the seventh over 7 factorial, and so on and so forth. But what do we notice? Well, let's see. This right here is exactly the series for cosine, right? Except instead of x, we have a theta. And then this right here is just the series for sine. And so this is equal to cosine of theta plus I times sine of theta. And so we're done. So we showed that e to the I theta is equal to cosine of theta plus I sine of theta, just using these power series representations. There's a bit of a subtlety here. This rearranging the terms part right here, you can't just always rearrange terms. The fact that we did rearrange these terms, or the fact that we're allowed to, is basically because all 3 of these series up here are absolutely convergent. So there's a little bit of details to be filled in there with that, but we're just gonna kind of leave it at that and move on. All right, so anyway, the upshot now is that we can use this theorem to convert between writing something as like 5 plus 2i and maybe something like e to the I theta, or r times e to the I theta. So for something like 2e to the I pi thirds, this is equal to 2 times cosine of pi thirds plus I times sine of pi thirds. And I'll draw my like pi thirds triangle right here. So this is like 1, 2, square root of 3. So cosine of pi thirds is a half. And then sine of pi thirds is root 3 over 2. And so this number right here is equal to just 1 plus I times the square root of 3. Conversely, you can go from something like this, like 5 minus 5i, and put it into like an r e to the I theta term, expression or whatever, or form, yeah. So a lot of times it can be helpful to just draw this in the complex plane. So here's 5, here's like minus 5i, and so here's 5 minus 5i. And so there's going to be like a distance to the origin for this guy, and then there's going to be an angle with the positive x-axis or real axis. So you could represent that angle like so, or you could just use a negative angle right here. So because it's symmetric, this angle is going to be negative negative pi fourths, Or if you wanted to represent it with a positive angle, it would be 2 pi minus pi fourths. What's that? 2 pi minus pi fourths. If you find a common denominator, that would be 8 pi over 4. So this is 7 pi fourths. And what would the radius be? Well, by the Pythagorean theorem, r squared is equal to a squared plus b squared. So 5 squared plus 5 squared. So that's 50. So r would be the square root of 50, which is 5 times the square root of 2. And so this would be 5 root 2 times e to the I times, I guess I'll write it as 7 pi fourths. Or you could use the negative angle, e to the I times negative pi fourths. Right, so you can always convert between like these two forms right here. And so the upshot is that complex numbers x plus iy can also be written as like r times e to the I theta, right? And in general, x plus iy is, you could write this as sorry, what am I trying to say here? Sorry, let me refer to my notes real quick, just so I don't. What exactly was I trying to say here? Sorry about this. Yeah, okay, yeah, so, oh, right. So, remember from before that x is equal to r cosine theta and y is equal to r sine of theta. And so you could just use that conversion right here. So x is r cosine theta and y is r sine theta. Then you can just pull out that r and you're left with cosine of theta plus r plus I sine of theta. And this is exactly what we just showed is equal to e to the I theta. All right. Anyway, what are the uses of this? Why would this be helpful? Multiplying numbers of the form x plus iy is a little bit tedious to do. Like if I wanted to square a number, like you could do that. If you wanted to cube a number, that'd be a little bit more annoying. Raise it to the fourth or multiply it by like 5 or 6 numbers or something like that. Automatically, it just becomes way more annoying. Adding 2 numbers of this form and getting it back into this form is very easy, but multiplying is very difficult. And so if you were to, for example, I forgot to delete this. Come on. Whatever. I'll just look at that. All right. So yeah, for example, if you wanted to multiply 2 numbers like this, 2 e to the I pi thirds times 4 e to the I pi fourths, you can basically just multiply like the magnitudes, the distance from the origin, and because of exponent rules, you're basically just adding the angles right here. So e to the I times pi thirds times e to the I pi fourths. Just by exponent rules, you end up getting this. And so if you add the angles, you just get 7 pi twelfths. And so geometrically, it looks like this. So this guy times this guy is going to equal this, or this point up here. So the magnitudes are multiplying and the angles are adding. So you're getting sort of further away from the positive x-axis. So angles add, magnitudes multiply, right? So if you're multiplying stuff or dividing or like whatever, it tends to be easier to be working with this form. And you might imagine multiplication kind of happens a lot with complex numbers. And if you're doing a lot of like addition, it might be more useful to be in this form, the x plus iy form. All right, so here's an example that sort of puts a lot of this stuff together. Let's find all solutions to x cubed equals 1. So this is kind of a harder question than most people would kind of think. So when I say all solutions, really I mean all complex solutions, because if I were really asking, find all real solutions to x cubed equals 1, then the only answer would just be x equals 1, right? However, with complex numbers, it's not so simple. So, right. All right, so basically what we need is, well, if we're going to represent x with r e to the I theta, we need this cubed to equal 1, right? So we'll just represent x as r e to the I theta. And so if we do this, this basically just tells us r cubed times e to the I times 3 theta is equal to 1. R cubed, that's your distance from the origin, right? So this is the magnitude. And how far is the number 1 away from the origin? It's just 1 away. So that tells us that r cubed has to equal 1. And this is a real number. And like I just said earlier, there's only one real number such that that real number cubed is equal to 1. And so our magnitude has to be 1. And then we basically just have e to the I times 3 theta is equal to 1. But you could also just say that this is like 1 times e to the I times 0, right? And so graphically, we're looking for an angle such that if I take that angle and multiply it by 3, or add it to itself 3 times, I get to the angle 0, or in general just a multiple of 2 pi. So graphically, these are the angles that we're going to be looking for. This is e to the I times 2 pi thirds, or e to the I times 4 pi thirds. If you were to take either of these angles, add it to itself 3 times, you're just going to get either like 2 pi or like a multiple of 2 pi. So basically, mathematically, what we need 3 theta to be a multiple of 2 pi. And so the angles in 0 to 2 pi that we would get this means that theta can be either 0, 2 pi thirds, or 4 pi thirds, which is basically just negative 2 pi thirds. Okay, so these numbers have a special name. These are called the third roots of unity. You might imagine that the fifth roots of unity are just the 5 solutions to x to the 5th equals 1. The roots of unity are just numbers, the complex numbers like on the unit circle, such that x to the n is equal to 1. So these are like the nth roots of unity. Here, this is for x cubed equals 1, so they're the third roots of unity. Okay. The 8th roots of unity look like the following. So they're just e to the I times theta, where your angle is just a multiple of pi fourths. So this guy, this guy, this. So there's 8 of them, right? Including this guy. All right, so 8th roots of unity looks like this. And so if you were to take any of these guys and raise it to the power of 8, you would end up multiplying 8 times this angle, and you get e to the I times 8 over 4 cancels to just 2. So you get 2 pi times k. And like we said before, multiples of 2 pi are really just an angle of 0. And so you just get 1. So those are your 8th roots of unity. And so here's a very important theorem in complex analysis. It says that any degree n polynomial has exactly n possibly repeated roots in the complex plane. And this polynomial, all these polynomials are going to be able to factor completely like this. So x minus r1 times x minus r2, etc., where r1, r2, etc. are just your roots. So for example, like something like x to the 5th plus 1, let's see, can you, so you can, yeah, okay, so something like x to the 5th plus 1, you would be able to factor that over the reals, but the coefficients might be terrible, and you wouldn't be able to factor it completely into like x minus something else. For like an easier example, something like x squared plus 1, you can't factor that over the real numbers, but you can factor it over the complex numbers because this is x plus I times x minus I. So basically, having the complex numbers there just adds this degree of freedom to you when it comes to like factoring and working with stuff. So yeah, basically complex analysis is very, very powerful. A lot of really nice sort of properties kind of happen with it. Real analysis is sort of like a subject full of like counterexamples, and like you expect something to be true, but it's not true. And complex analysis is sort of the exact opposite of that almost, where you just get these like crazy hyper powerful theorems that just kind of tell you that everything works out super nicely. It's like, oh yeah, you can always factor stuff. You can always, do whatever. I can't think of like other examples off the top of my head, but there's a lot of powerful tools in complex analysis. All right. Anyway, I just wanted to do one sort of random example, which is just completing the square. So something like x squared plus 8x plus 25 equals 0. Let's just like solve it. Actually, let me just kind of do it on the fly as opposed to just showing you stuff. So x squared plus 8x plus 25 equals 0. Okay, so completing the square is like when you have, it's like if you have like x plus a squared plus b squared equals 0 or something, or just plus b equals 0, I guess. So we want to basically like put this guy into this form. And if you were to like sort of expand this out, this is like x squared plus 2ax plus a squared. And then just these guys make up your constant over here. And if 2ax is equal to ax, then a is just going to be half of whatever this number is. And so we're going to pull apart a squared from the 25, and that's going to break down, that 25 is going to break down into a squared plus whatever b is left over. So anyway, how does that happen? 8x, half of 8 is 4, and so we're going to write this as, this is x plus, it's going to factor as like x plus 4 squared 2 steps later. Right, but x plus 4 squared is x squared plus 8x plus 16. And so we're borrowing 16 from the 25, so there's 9 left over. All right, so we get this. And if we're just trying to solve this, then you can bring the 9 over. So x plus 4 squared equals -9. And then take a square root. You get x plus 4 equals the square root of -9, which is just 3i. And so x, And because we're taking a square root, we should also account for both the positive and negative square roots. And so we get plus or minus 3i here. And so x is equal to negative 4 plus or minus 3i. And how do I say? So also notice that I mean this might feel like a very like roundabout like way of doing this when you could always just do the quadratic formula, right? Personally, I kind of think that this is a little bit quicker with easier to work with polynomials than doing the quadratic formula. The quadratic formula is just a surefire like formula that always works for these things. So it's x equals negative b plus or minus square root of b squared minus 4ac all over 2a. So this to me is very tedious. This to me is sort of more intuitive. And so you could do this. This is going to be a plus or minus, all right, 64, that's minus 100, so negative 36. And so that's plus or minus 6i all over 2, or negative 4 plus or minus 3i. So you're getting the same thing. These steps to me are not quite as tedious as just doing like the multiplication and subtracting and stuff like that. So I don't know, this can kind of just be like a short sort of quick trick that you can use. Completing the square comes up a lot. It's just kind of a useful thing. Anyway, it's sort of a weird random example to end on. Probably thematically made more sense to end on the giant important theorem. But anyway, that's it. So I hope you guys found that interesting. Hope you saw some of the connections to the class that we have going on. And yeah, if you guys are curious about anything else in this subject, or if there's anything else that you kind of want to know about, please let me know and I'm happy to cover it.